Hi everyone, I'm Andreas and I'm presenting to you our vision paper on mining high-resolution Earth observation data cubes. And let me emphasize, this is not a research paper, this is a vision and challenge paper. So in this talk and in the paper, you will not find any solutions, you will not find any results. All you will find are problems and challenges. And our vision in this paper is to mine Earth observation data cubes, which are tensors of spatiotemporal information, often observed from satellites, and often having trillions and even quadrillions of observations. And these very large data sets create challenges for us as the spatiotemporal database community, challenges in managing the data, mining the data, and also for spatiotemporal prediction. And this work is a collaboration between myself, Dr. Konrad Wessels, and Dr. Pfoser at George Mason University. And Dr. Pfoser and I, we are computer scientists, and Dr. Wessels is an expert in remote sensing. All right, a colleague of mine always said that any presentation should start with a joke. And I tried to come up with something funny, but I'm German. So instead of saying something funny, let's play a game. Let's play Where's Waldo? Which is a very simple game where your goal is to look at an image and find this guy here, whose name is Waldo. Where's Waldo? Level 1. Does anybody see Waldo? Anyone?
Yes, yes, yes.
Who said that?
Me, I see him,
Okay, very good, Fluffy. So where do you see Waldo?
He's in the top right.
Very good, you found Waldo, well done. Okay, let's try a harder example. Let's look at this image here, which is taken from the original Where's Waldo book. Do you guys see Waldo? I'll give you a few seconds. Look closely. Okay, time's up. If you want more time, of course, you can pause the video and look more closely. Have you found Waldo, Fluffy?
No, I haven't.
Okay, you can keep looking at the slide and let me know if you found him, okay?
Okay.
So how about you? Have you found Waldo? If yes, well done. And in that case, I would like to go to level 3. And on the next slide, I once again want you to find Waldo. Do you see him? And I'm even going up one more level. Instead of not knowing where to look, the challenge might also be not knowing when to look. And what we see here is Earth recorded every 2 hours. So every frame that you see is an Earth observation taking in 2 hours interval. And now imagine you are looking for something like a forest fire, like a flooding, and you don't even know when to look. So now the challenge is we want to find something in our spatiotemporal data, but we don't know when to look and we don't know where to look. Now, why is this a challenge and vision for the spatiotemporal database community? The reason is that there is a lot of Earth observation data out there. There are trillions of pixels being collected every single day. Let me give you an example. The Worldview 3 satellite has a 33 centimeter per pixel resolution, which means there are more than 10 million pixels per square kilometer, and Worldview 3 covers 680,000 kilometers a day, and doing the math, that means that this satellite alone creates more than 7 trillion pixels every day. But there are other satellites out there as well. For example, there is the Landsat and the Sentinel-2 program, which each coordinate up to 4 satellites. And by having more satellites, the advantage is that the same area will be visited more frequently. And the great thing about this data is that it is publicly and freely available And in addition to image data, there's also different types of Earth observation data. For example, there are the MERA-2 data cubes, which do not contain visual images. They contain temperature, humidity, precipitation, and many other environmental factors, which are measured at 50 kilometer per pixel resolution, but have been measured across the world hourly since 1979. And again, this data is also publicly and freely available. So we have these very large data sets that observe our planet over time. Now, abstractly speaking, we can describe all these observations in a three-mode tensor of latitude, longitude, and time. So every observation that we have has a latitude value on a spatial grid, a corresponding longitude value, and a point in time, which can be a day or an hour. And if we take all these observations together, we get a Earth observation data cube, as shown here on the right. And Earth observation data cubes are not new. They have been used in the remote sensing community for a long time. But what is becoming challenging for these Earth observation data cubes is their size. Let me give you an example. For the Worldview 3 satellite, we have 45 million latitude values, 45 million longitude values, and the dataset covers 3,000 days, meaning that our tensor has a total of more than 6 quintillion cells. So this tensor on the right has more than 6 quintillion cells for Worldview 3. You might be confused now because a few slides ago I said the data collected by Worldview 3 is in the quadrillions. Now I'm suddenly saying it's in the quintillions. The reason is that this data cube is sparse. The observations, the actual latitude, longitude, time triples for which we have an observation is much smaller than the total possible longitude, latitude, time triples. And now you have an idea of what I mean when I say Earth observation data cube. Now let me go to my first vision. My first vision is to get a unified Earth observation data cube. I talked about Worldview 3, but there are other satellites out there which may have a lower spatial resolution, but they may have more satellites that can complement each other. And a good example is Sentinel-2. There are also other satellite constellations, some of which have hundreds of small satellites. Each of them produces a smaller data set, but again, instead of having 1 or 4 of those, we may have hundreds of these satellites in their constellation. But there are also other types of Earth observations, for example, as collected by drones. And let me give you an example. What you see here is the soccer field at George Mason University after our department soccer game, where students play against faculty. And we had a drone that was observing our soccer game. And what you can see here is about 50 of our students forming the letters GGS. In addition to having Earth observations from satellites, what is now possible is for individual users like you and me to create high-resolution Earth observation data. And a possible vision is that in some years, we may be dealing with volunteered Earth observation information. Just like volunteered geographical information, VGI, we may soon have volunteered Earth observation information by individual people and their drones making their Earth observation data available. Going back to our vision of unifying all these different types of sources of Earth observations into a unified data cube, we also want to add drones having volunteered Earth observation information in them. And now one vision is to create a unified data cube, a supercube, which understands which cell of one data cube corresponds to another cell in another data cube. And the goal is to create this supercube which captures information of the big satellites, but it also captures data from the small satellite constellations, and it even captures information contributed by all those individuals who contribute volunteered Earth observation information. The vision is to have one supercube, a unified Earth observation data cube, which contains all the Earth observation information. And towards this vision, there are a few challenges. The first challenge is what remote sensing calls registration, to map the cells of one data cube to another data cube, meaning we need to align the potentially different grids of multiple data cubes, which may have different resolutions, which might not be perfectly aligned. There might be an offset, there might be overlap between different cells. And the good news is that the remote sensing community already has great solutions for co-registration of images. For example, what we see here is data from harmonized Landsat Sentinel-2 HLS data. And we have also obtained data from the United States Geological Survey, which has a national land cover database, which regularly updates for each pixel in the United States the corresponding land cover. And what you see on the right is this data set co-registered with the Earth observation data. So now what we have is a joint data set where for each pixel we have both the spectral features, in this case grayscale, and also information about the land cover. And now this is great because now in addition to having these trillions of pixels, we also have a ground truth for each of these pixels. For each pixel we now have a ground truth. What was the land cover of this pixel at this time? So there are already solutions for co-registration, and where the spatio-temporal database community can contribute substantially is the challenge of making this co-registration scalable, working with these trillion and quadrillion sized Earth observation data cubes. And this requires managing all this data efficiently, being able to query the data efficiently, but now looking at trillions of locations on Earth and having quadrillions of different observations in different locations at different times. That is one challenge towards a unified Earth observation data cube. A second challenge is the problem of uncertainty, because these different sensors, satellites and drones that we have, they may produce obsolete, inconsistent or contradicting data. And solutions are needed to assess this uncertainty such that the user knows, hey, look, this observation was confirmed by 3 satellites and 1 drone. However, this pixel here, it was only seen once, and that was a while ago. So, hey, I'm less certain about the correctness of this observation in my data set. A third challenge that we have is imputation. As I mentioned, these data cubes are going to be sparse. And now a question is, given this location at a point in time, we don't have an observation, but can we impute the missing observation? Can we estimate what this location would have looked like in terms of spectral features, in terms of temperature and wind speed, if we had had any observations? And one way how the spatio-temporal database community and the spatial computing community could approach this problem could be using tensor factorization and using canonical decomposition or a CanDecomp. We would decompose this data cube into 3 matrices, each having k latent features for time, for latitude, and for longitude, meaning that we can now represent each point in time as a vector of k features. And in a Netflix movie recommender system style approach, one could use this factorized representation of the data cube, re-multiply the factorized version again to get an estimated data cube hat D, which will have missing values imputed. But this is just a naive approach using tensor factorization to predict missing values. So there's certainly better ways to do spatiotemporal imputation of Earth observation data cubes, and that is another challenge. Now, let me talk about the second vision, which is more related to the little game that we played in the beginning of this talk, Earth-wide object or event detection. In a nutshell, the problem of finding Waldo in our Earth observation data cubes, which span the whole planet and may span years of data. And now when I say Waldo, you can see Waldo as a variable, which may be things like forest fire, flooding, and anthropogenic events, such as unexpected building of a construction site. And now the challenge here is to find objects or events, let's say a forest fire, without knowing where and when to look. So now the challenge is to find this needle in a haystack. We have the whole planet over time where we are searching, and we are looking for this one little true positive. And whereas we have millions, billions, trillions of true negatives. So the new challenge here is that, well, given an image of a forest fire and given an image of a non-forest fire, we can find good solutions to classify what is a forest fire, what is not a forest fire, which means we have good solutions to classify what is a needle and what is a hay straw. But the challenge of finding the needle in the haystack when you have millions of negative examples but few positive examples, that is a big challenge. So in summary, the new challenge is that we want to find objects or events, but without any a priori knowledge of when and where to look for these objects. Then, as a third vision, we also want to go one step ahead, take our Earth observation data cubes, and make the steps toward predictions. Say we have an Earth observation data cube until time t, and we now want to predict the next times, the slices of the data cube at time t plus 1, the future of the data cube, and since the data cube pertains to Earth, the future of Earth itself. And again, using the example of using tensor factorization, we can turn our data cube into a factorized representation like we did before, and now we can use this factorized representation to predict the time features at the future times. We can use solutions for time series prediction to predict these future latent attributes of time, which will then, by multiplying the latent representation back into the full data cube, will give us an estimation of what the future steps in time in our data cube will look like. And once again, this is just an idea towards a solution. There might be better solutions out there than using a tensor factorization. And that was the third vision, predicting future Earth. And those were our three visions. So let me just summarize what we have seen. We have these Earth observation data sets available. There are these satellites generating trillions of pixels every day, and we can download this data. We can access this data. It is made available to us. And this creates some very interesting challenges for the SSTD community. The first challenge is data management. How can we manage such a unified Earth observation data cube that has data from multiple sources, from multiple sensors? How can we join these data sets together, and how to handle uncertain data, and also how to handle missing observations by imputing missing values? The second vision was the vision of broad time and area Earth observation data cube mining, meaning we have this huge data cube over the whole Earth over a long period of time, and we want to find interesting patterns in the data, which could be forest fires, floodings, or any other event. But the challenge is that we do not know a priori where we will find what we are looking for and when we will find what we are looking for. The third vision was not just finding, mining, querying information of an existing unified Earth observation data cube, but going the step further and predicting the future Earth observation data cube, predicting what our planet will look like in the next hour, in the next day, in the next years. And with that, let me thank you for your attention. Do you have any questions?
Found him.
Oh, Fluffy, what?
I found him. He's...
Wait. Don't tell them. You're going to spoil it for everybody else.
Okay, I won't tell it, but I found him.
Yes, very good.